Hi, welcome back. Today we're going to talk more about applications of partial derivatives. And one of the things we're going to look at is how can we use partial derivatives to help us understand the parts of conic sections. And you might recall this equation from pre-cal where g is a function of x and y because conic sections are a function of x and y. And where we have our little equation right here. But this little piece right here where we have c, x, and y together tells us that this is a rotated conic section right there. And so today we're going to look at how we can use partial derivatives to determine how we can graph a conic section that's been rotated. So assuming that these are level curves, okay? Now remember, level curve is just a flat two-dimensional image of a slice through a surface. So the first thing we're going to do is we're going to find the partial derivatives of g in terms of x and y. So if I find the partial with respect to x, that's not too bad. This just becomes 2ax plus cy plus d. If I find the partial with respect to y, we're going to get 2by plus cx plus e. And now we're going to find out, well, how can we use these partial derivatives to find the equations of the lines that line the diameters of an ellipse? So let's take a look at what a rotated ellipse kind of looks like. I have this diameter right here. There's my diameter. And I have, of course, another diameter. The diameters are the longest lengthwise and longest, of course, and the shortest distance. So those are my diameters of my ellipse. So we can find those by just taking your partials and you're just going to set them equal to 0. So the first thing we do is we're going to set the partial with respect to x equal to 0. And that's going to give me 0 equals 2ax plus cy plus d. Solving for y is a line. I get y equals, what's that become? Negative 2a over y x minus d over c. And that would be the equation of one of your diameters. To get the other one, we set g of y equals to 0. The derivative with respect to y equals to 0. And that's going to be 0 equals 2 by plus cx plus e equals to 0. And solving for y, we would get negative cx over 2b minus e over 2b. Or not 2b. And that would be the equation of both of our diameters. And we would get those. Alright, so for the next one, ready? Well, what's so special about the diameters? Well, one, the diameters, they help us find the center of the ellipse. Well, how can we do that? Well, diameters must intersect. We find the intersection. And we'll take a look at an example in a little bit. But two, they can also determine to find the endpoint or to find the maximum values. These partials will help us find the excuse me, the maximum and minimum values. Right here. So let's take a look here. Well, if we find the equation of both linear diameters, how can we use that system, and what can we use, and what can we find from them? Well, of course, we just talked about we can find the center. So if we just, to get the center, we just set the two partials and solve. And we want to find that intersection. But let's talk about the absolute maximum and minimum. What about the maximum and minimum values? Well, we know from calculus, if we want to find the absolute maximum minimums, we set our critical numbers, we find our critical numbers, and we set them equal to 0. Well, how does that help us find the maximum values of our conic section here, of our ellipse? Well, if we look at our conic section right here, where do my maximum values occur? Well, remember, they don't occur along the diameter. A maximum, remember, if I'm looking for a maximum, In partials, we're only looking at the change of x's and the change in y's only. So right here, if I find my maximum distance here, well, that is a change of x. That's more of a corresponding between x and y. They're together. But if I want to find the partial, if I'm looking at the partials, they're only looking at the change in the y values and the change in x values. So when I look at my graph right here, that's going to be my maximum value, or my maximum height, basically right there. And in calculus, we always said, well, this is where the derivative, or the slope, is equal to 0. I have a minimum value down here, my minimum height. And again, we always said that the slope was equal to 0. In other words, basically like saying dy is 0, the change in y values are 0. The change in y values are 0. But I have two more. I also have right here. This is also a maximum. This is my maximum distance to the right. And in this case right here, we said the slope does not exist. And last year we would say dx is 0. The change in our x's was 0. And likewise, we have a point over here where we have a minimum value, which is in this case, we have a maximum distance on the left, okay? And the same idea, the slope here does not exist. So we can find these if we set our partials equal to 0, because what that's going to give us is, excuse me, what that's going to find for us is those critical numbers, in terms of the change in x's and the change in y values. Okay. So let's see here. So we're given a rotated ellipse. We're asked to find the center and the maximum minimum x values and the maximum minimum y values, and then sketch the graph. So let's see here. So we're just going to go ahead and find the center here. To do the center, my rule says find the partials. We get 2x, that's 0, 0, minus 8, plus that becomes 2y, and I have to set the equal to 0, so I get 2x minus 8 plus 2y equals 0. Do the same thing with my y's. This becomes 8y plus 8 plus 2x, and if I set that equal to 0, we get 0 equals 8y plus 8 plus 2y, and this is just a system to solve, so we're just going to go ahead and solve that system. And what you wind up with is 20/3 and -8/3, and that would be your center. You guys can go and solve that any way you want to. All right, going to part 2, we're going to take a look at how we find the maximum y values. Okay, it's a little bit longer, so we'll have fun there. Bye-bye.